All right, one more. So this will be the final chapter. So there are. Let me go back up to the top. Here we go. Final chapter. We're talking about applications and processing. Very important details about microstructural features. What happens with mechanical properties as a function of temperature and processing. So we have examples of the mechanical properties for brittle polymer, very low megapascals, nothing in the many hundreds or thousands, very, very low, under 100, typically more often around the 20s to 40s. Normal plastic is plastic behaving. The elastomers are the stretchiest, think elastic and things like that, rubber bands. The elastomers just stretch under any kind of force being applied, and from there they change significantly. So there's a lot of stuff going on there. There's a lot of stuff going on. So the fracture strengths are on the order of 10% those of metals. So they're very low fracture strengths. They deform more like 1,000% of what metals do. So the strain is significant in, especially elastomers. They become multiple times their own original length in some circumstances before they actually fail. So that's their stress strain behavior by comparison. So some of them are a little more brittle like, some of them are a little more plastic like. So something like a Delrin is going to be more brittle like, a little less plastic like. And the brittle failure happens with highly aligned cross-linked polymers. So that linear example that I was talking to you about versus network polymers that stretch and stretch and stretch, and they have lots of room to change. Near failure, they are very different. The networks stretched near failure are very different in their behavior. So the mechanisms for deformation are also quite a bit different. There is necking that happens in these polymers under tension for plastic behaving plastics rather than brittle behaving plastics. And there is an unload and reload that is almost a straight line down for plastics. So they behave very consistently. So the undeformed structure, there's an amorphous region that stretches out, and aligns, and then begins to tear these blocks apart internally. And that's what creates the necking phenomena until they ultimately come apart and unravel completely near failure. So there is sometimes a method, for instance, like fishing line is a monofilament fishing line, stretches the polymers prior to use and aligns the chains in the stretching direction. What that does is that increases the elastic modulus in the stretching direction. That increases the tensile strength in the stretching direction, but it decreases ductility. So it's more elastic, but a lot less ductile. So it's not going to be flexible and want to bend very well. So it's going to be brittle in that sense. But in the case of something like a fishing line, a monofilament, you want a really strong singular filament rather than some kind of braided line. Those combination of properties, higher elastic modulus, higher tensile strength, those are desired. Decreased ductility is acceptable because you're not trying to bend and flex it. You're trying to hold a high level of tension on it with some elastic behavior because of the jerking of the fish at the other end, or the firm hold that that really old boot has at the bottom of the lake, right? So the annealing can be done after drawing that will decrease the chain alignment. It will reverse some of the effects of drawing. It will reduce the elasticity, reduce the tensile strength, and increase the ductility. And that is different from a little bit different, but not hugely different from the way that something like cold working in metals happens. So cold working is usually not by drawing or pulling very hard on that filament until partial failure to pre-stretch it. It's really done to so those monofilament lines start out as thicker diameter lines. They get pulled, meaning drawn, into those thinner lines, but they become stronger as a result. So the annealing can help to realign the chaos, or bring back some of the chaos and undo some of the chain alignment in the polymers. But they can also be annealed to reverse those effects, just like metals can be annealed to reverse the effects of cold working. So that should make some sense. And the mechanisms of deformation in elastomers are fairly straightforward, but they are three different behaviors. So the brittle is aligned, cross-linked, and network polymers. Plastic is typically semi-crystalline, as shown on the previous slides, because that's what this is doing. So it's starting out undeformed. There's a lot of chaos and lack of arrangement. There's the amorphous and crystalline regions, and as they load, they stretch and align, then they start to separate, and so the monofilament is going to be in this kind of region. But that's plastic behaving, and elastomers have even more examples. So they have lots of these sort of coiled chains, so you can think of them as a box of slinkies, and they're all tangled up together. So if you pull at one end and somebody else holds the other end, you're just going to pull, and all these different slinkies are going to unravel at different times. But then if you stretch Slinky too far, it's going to take him years to recover. What did it take him? 10 years before he could do another movie? Good grief. Was it 20, 30 years? I don't know. It was a long time. Yeah, a lot of deformation that happens, and it's mostly all reversible because it's all these long coiled coils of coils that are uncoiling and allowing all of that energy to be stored by organizing or lining up those chains. And that's the thermodynamic reality. Once those chains become lighter, become straightened out, they are still cross-linked, but it becomes then like the brittle failing chain-linked polymers. So the elastomers have these looped coils and coils of coils. So that organizing of the chains, that alignment, actually cools down the rubber. So because of the other thermodynamic properties. So if you work a rubber band back and forth, and you stretch it and unstretch it, stretch it and unstretch it, and you do that a bunch of times, what you're actually going to end up doing is dropping the temperature of the polymer as a result of that. So rather than increasing the temperature like you do with steel, where you're pounding kinetic energy into the material and everything's warming up and heating up, the elastomers are unique in this sense that they actually cool down because you are organizing or taking away the disorder from the system, and that has to balance the temperature change. You guys will learn more about that in the thermodynamics, so we'll have to ask your professor about that. Thermoplastics are very, very important. Thermoplastics versus thermal sets. Thermoplastics have a little bit of cross-linking. They're ductile. They soften when heating. Polyethylene, polypropylene, polycarbonate, polystyrene are examples of these. So if you put a polystyrene cup, ye old standby, if you put your ramen noodles, since anybody shopping at Walmart that isn't making 300 million a year is probably buying ramen noodles. The polystyrene cup, if you leave it in there too long, it has a tendency to sort of melt and slump over, and then that's how fires start, because the liquid starts to pour out of the container. Even some of the polyethylene containers and things that have been used for those, the materials can deform if they've been microwaved too long. They create a leak, the water leaks out, then the polymer is exposed to the microwave without the liquid to sort of help moderate the temperature increases, and it can catch fire inside the microwave. It's super exciting, but a great way to get yourself kicked out of the dorms, so don't try that at home. So thermoplastics soften with heating. If your car was made of thermoplastics, you would get in it in Phoenix and your steering wheel would be in the floor as a puddle and things like that. So we don't use thermoplastics in high temp applications. We use thermosets. They have significant high degree of cross-linking, 10 to 50% of the repeat units. They're hard and brittle typically, so they don't soften with heating. They're vulcanized rubber, epoxies, polyester resins, phenolic resins, things of that nature. So we don't use a lot of those kind of applications. That's why things like you take a billiard ball outside and you leave it in the sun and nothing happens except it gets really warm. That's an example of a thermal set. So that's a resin, and I think those are phenolic resins. Pretty sure they're phenolic resins. Can't remember exactly offhand, but anyway, molecular weight goes up, temperature goes up this way. There's a crystalline solid region, low temp, low molecular weight, high molecular weight, low temp, partially crystalline solid, high temperature, low molecular weight, liquid, viscous liquid, and the intermediate molecular weight, high temperature range. Tough plastics, meaning high molecular weight and also high melting temp, are tough plastics. So tough plastics and rubber are used in a lot of automotive applications because of those regions. They have to be in a high temperature, high abuse environment where they need to be very, very tough. So there are some tough plastics in those senses. The influence of temperature and the strain rate also become important. So as the temperature decreases, the stiffness increases. So cold plastics tend to be very stiff. The tensile strength increases, and they decrease in ductility. So they become more brittle-like at low temperatures, especially if they get to be really, really low temperatures, down below freezing. Typically, they become very brittle. You know this if you have pulled a plastic dish out of, especially some of the newer ones that they're trying to make with bamboo fiber reinforced, super sustainable, actually grows new forests when you use these kinds of cookware. Especially at cold temperatures, they become exceptionally brittle, and as a result, they don't carry some of the same behaviors of fiber reinforced plastics that we would know from elsewhere in other industries. They become very brittle and they tend to shatter rather than simply absorbing the blow. So very low toughness. Increasing temperature does the opposite of that. So it decreases the stiffness. They become less in tensile strength, they become more pliable in ductility. So PMMA, i.e. plexiglass, becomes brittle at cold temperatures. At higher temperatures, it tends to stretch and flow. So the way that behaves is wildly different based on the temperature and environment that it's in. So this is the reason why it's especially hard to make something like plexiglass. This is part of the reason why the Department of Traffic in almost all states will give you, like, maybe not in Montana, but probably still because they have low temperatures, but most other places in the US, if you have plexiglass windows, because you think you're driving a race car and it's actually just a Honda Civic and you're lying to yourself because that makes you feel better, the plexiglass windows are not consistent in their behavior. They have wildly differing physical properties, and they can become problematic in an accident because of that unpredictability, compared to glass, which is much more stable, sort of regardless of what temperature it is. Glass is a much harder crystalline material. So also the strain rate. As the strain rate increases, it's the same effect as decreasing temperature. So if you load a polymer very quickly, if you yank on a rubber band really fast, you have a higher likelihood of making it behave stiffer. Again, it physically drops the temperature of the polymer a little bit. And so if you yank something like an elastomer really hard, then you have a decreased ductility, you have an increased tensile strength, and an increased stiffness of the material, because the strain rate, the rate at which you are changing the length of the polymer, as that goes up significantly, it's the same kind of thing as decreasing temperature. So increasing temperature has the opposite effect, or slowing the strain rate has the opposite effect. This is part of the reason also why, for instance, the guys that do drifting cars professionally, they tend to enter a corner very aggressively, and what they're doing to those polymer chains in the tires is they are putting them under a very high strain rate, meaning they are suddenly subjecting them to a very significant change in the strain, and that creates a situation where the polymer becomes more brittle, and they're able to shear off layers of that polymer because it crystallizes at that temperature. And so the reason why they seem like they are sliding out of control is because they are in fact sliding out of control, but in a sort of controlled manner some of the time. This also has to do with what's called a glass transition temperature and the way that some of these things behave. So a lot of polymers behave one way at a certain temperature range, behave another way at another temperature range, because their properties and their stiffness changes, their physical properties change above these transition temperatures. So at the melting temperature, glass becomes a liquid. The semicrystalline solids become liquid as well, so the crystalline solids. But glass has a sharp change in the specific volume, so it heats. As soon as it becomes the glass transition temperature, it suddenly starts changing in volume significantly. And then above the melting temperature, it's liquid. The semicrystalline solids have a little less sharp of a knee in the curve, but they do have a glass transition temperature such that they become more glass-like. They become more apt to flow and remold. Crystalline solids tend to be much more linear in their behavior, comparatively. So The chain stiffness is increased by the presence of bulky side groups, polar side groups, or side groups that are basically interacting. So bulky side groups because they tangle up like a box of cords or strings. The polar side groups are the opposite attracts principle. So charge differences that attract each other, and the chain double bonds and aromatic chain groups that again become entanglement buddies in the same kind of sense. The regularity of the repeat units of the arrangement also affects the melting temperature, but not the glass transition temperature. So there's a bunch of different parameters that we can point to as far as how the behavior works and what these things do. So the stress relaxation test is where you have a strain up to epsilon naught, and then you let go. You take that tension off, you take that load off, and you look at what the stress does over the course of time. So there's a relaxation modulus. This is especially important for polymers that are designed to take up stress and, as a result, strain from the movement of a system, like foot pads that you would put on a noisy piece of equipment that vibrates. Something to dampen that vibration is intentionally chosen because it has a meaningful relaxation modulus relative to the strain that's being applied as a result of the stress. So it's not as simple as just putting rubber foot pads underneath something. The durometer of the rubber, and therefore its relaxation modulus, changes, and therefore one will work really well, one will work not so well. So there's a large increase in the relaxation modulus for temperatures above the glass transition temperature because of how those physical properties change. So in the case of something like amorphous polystyrene, there's a glass transition temperature just below 100 C, right? So amorphous polystyrene, think styrofoam that you've interacted with. Below the melting temperature, by the time you reach the melting temperature of water, polystyrene starts to do some weird stuff. It enters the transition region, and then if it goes too high, you try to boil water or add boiling water that stayed boiling too long, it's going to take that into the transition region. If you could get it up to about 150, 160, almost 170 C there, you're going to get it into a liquid region and turn it back into a liquid. So there's a lot of changes, but it's only a rigid solid down below about in the case of glass transition around 100 C for polystyrene. So that's why we can use hot stuff in it, but not too hot and not for too long. So we wouldn't do that for PVC because that's not going to be able to contain it. You can soften PVC significantly by putting it in the presence of a boiling agent. That's how they bend PVC very often. Or they heat it with a torch and try to catch it on fire. Really, either method is acceptable according to the YouTubes. Polycarbonate. That one works for cleaning cookware and things like that. So you'll see a lot of polycarbonate dish scrapers that seem like they're almost indestructible. That's why. Low density polyethylene glass transition temperature can be about minus 110 C, minus 90 C for high density polyethylene. So it's important to understand how they're going to behave for an end application. So we've seen crack propagation and fault propagation in metals. In polymers, you have voids or pockets form where the polymer separates. Then you get this narrowing area, so you get almost hundreds and hundreds and hundreds of necking phenomena forming as those fibrillar bridges crack. As that crack propagates, those fibrillar bridges become smaller, and those microvoids start to join together, and you get failure of the material. So the crack propagation is the continual formation of those voids as the total number of chains gets smaller and smaller and smaller. This is why polymers tend to start failing and then unzip almost as soon as something starts to fail. It fails very catastrophically. This is why we don't use just a woven, we use woven nylon with many layers to make seat belts, rather than just nylon fabric and sewing a few layers together, because that prevents this form of fault propagation from happening. So now you know why seat belts are woven nylon in the way that they are, to prevent and reinforce against this specific failure mechanism. So the polymer formation, we talked a little bit about the addition concepts. So it's usually addition, chain addition. There's also condensation, which involves water coming out of the reaction because you have a hydroxyl group at one end of a monomer and a hydrogen at another end, and those two come together to release H2O, and you get a covalent bond across to replace it. So chain polymerization is the radical example that we used. So it starts with an initiator, with one radical gets in there and whole pot's gone. That's how it goes. Termination becomes two radicals collide together and cancel each other out. So the there can also be disprotonation or combination that happens there. So the condensation is, yeah, what I just described here. So they use an example of hexamethylene diamine and adipic acid. So you have an acid base reaction, you have water come off of that, and a nylon is born. This becomes kind of the backbone for a lot of the kinds of stuff that we do. So there are additives that can be included, fillers that change mechanical properties, processability, durability, adds resistance to UV damage, all sorts of things. So they're added to improve physical properties like abrasion resistance, toughness, and decreased cost. Carbon black for the case of coloring or silica gel. Maybe they need some degree of absorbency or cushion, or they need maybe wood flour because of, again, trying to lower cost. Glass, limestone, talc, if they want to keep the plastics from getting sticky. So there's a lot of examples of some exotic cars, Ferrari, where they make their buttons out of just garbage plastic that they didn't use the right kinds of fillers for, and so they become tacky and sticky and disgusting, and so yeah, they become very difficult things to live with as a result. And then plasticizers, everybody's up in arms about BPA. Then the EPA will regulate out the BPA and nobody can use it, and then they'll come out with BPB, and then everybody will get up in arms with BPB. And then they'll go to BPC, and that just is going to continue because there's gazillions of versions of molecules, You get rid of one of them and they're going to make another different one, and it'll take another 30 years before somebody figures out, hey, those are bad. So yeah, plasticizers are an example of something that helps reduce the glass transition temperature to make it easier to process, therefore taking less energy, therefore cheaper to manufacture. Cheaper plastics meaning lower prices at Walmart, because people are grumping about prices. They want cheaper prices, but then they want more expensive processing. So those two things can't happen at the same time, unless you increase supply and productivity. So we won't go into full economics because that's a whole other class. And yeah, it's going to be, that's a whole other class. That's a big one. So they transform a brittle polymer into a ductile one, and that allows for things like PVC to be more flexible and pliable, a little bit more ductile. So it's important to use those, but then those same plasticizers can also be leached out by the liquid, and therefore end up in stuff that we eat and drink and all sorts of things. So polymers are great. Also, polymers are terrible because of the processing requirements. So there's that. There are stabilizers. So antioxidants and UV protectants are big, especially for things like rubber seals that are going to be in a UV environment. If you don't treat them with UV protectants and you don't include those, you're going to have products that are prone to early premature failure because of interaction with sunlight. So on an exterior window seal for a building that has a lot of glass windows, that would be a bad thing to have. You don't want that, introducing all kinds of water leaks and weirdness. Lubricants added to allow easier processing. Polymers allowed them to slide through the dyes more easily, lowering, again, energy requirements, facilitating a little higher throughput. Sodium stearate is an example. It's also, there are several stearates that they add in all kinds of soaps and hand cleaners and surface cleaners and all sorts of things to act as a lubricant. Colorants, dyes and pigments, all of those sorts of things. So all this stuff, we want our plastics to be colorful and bright and fun, but also somehow not have anything bad in them ever. It's essentially a pipe dream at this point in time. There's always going to be something that could have an adverse effect. But then again, if you had a bowl that was made of wood and the wood was carved out of a tree that was grown in a place where you had lots of weed killers being used, then that would all be present and stored in the wood, and that would leach into your food also. So wait till they get a hold of those kind of facts, because yeah, then all of the crazy haired people will have even more things to yell and scream and throw temper tantrums all over TikTok, because apparently that's what TikTok is for. Adults to act like 3-year-olds. It's really, really interesting. The flame retardants becomes especially important. So things like drapes in hotels all are required to meet a certain flame retardant standard. They're all made of, at this point, mostly plastic based fabrics, and those fabrics must have a high degree of flame retardant. So typically things like chlorine, fluorine, and boron. So fluorinated and boronated polymers. Thermoplastics can be reversibly cooled and reheated, i.e. recycled, so they can be heated until softened and reshaped as desired. Polyethylene, polypropylene, polystyrene are examples of these. So plastics that we can recycle, whether we actually recycle them effectively or not, that's a different lesson. for a different day. The thermosets are forming a molecular network when they're heated and there's an actual reaction. They don't melt when they're heated, so they tend to be stable under temperature. And a prepolymer molded into the desired shape and then heated gives you the desired shape and the chemical reaction form. So something like a urethane or an epoxy. So think paints and coatings and things, when they bake on an epoxy paint to a tub surface or something like that. Very hard. It is a polymer, but it's very hard. It's possible to scratch, but it's tough for a plastic. And it's even the urethane of your bumper. You can't just go on there with a soldering iron and cover up your boo-boo when you accidentally parked in the cart return because you were like somebody I knew that thought they saw somebody that they dated one time, and so somehow that automatically means parking in a cart return, because probably some people just shouldn't be driving ever. So yeah, urethanes are not repairable with heat. You can't like plastic weld them back the way they were. That it just doesn't work that way. So you can add a thermoplastic polymer to fill in cracks in a urethane bumper or a urethane part, but you can't fuse back together the urethane ever again. So the best you can do is still a patch. Plastics are often compression molded. This is probably a large part of it, but there's injection molded is the probably by far and away the largest of anything is going to be injection molded. So polymers are added into a mold cavity. The mold is heated, then it stamps it together. The fluid forms the shape of the mold. Injection molding is more like this, where you have a feed hopper, you have a ram, you have a spreader, or you have it's mostly the injection type has rams, and then you have a heating chamber region and the spreader that evenly distributes out the pellets so that you have elimination of any gases or anything like that. The mold cavity gets filled and the material displaces the air, assumes the shape of the mold, then the mold gets separated and the parts come out. There are extrusion processes as well. So parts of this are like the 3D printers. Those are typically not an extruder head. There have been a couple people that have designed something like an extruder head for some very large scale industrial applications. But what this does is allow for different shaping dies. You feed stuff into a hopper, the turning screw runs the material down a barrel. There's a compression region because the diameter gets a little thicker for this type of material. This way there's less free space, and you become more forceful and increase the pressure as you go along in order to force it out the shaping die. You can make tubing, pipes, filaments, sheets, films, as well as structural parts. So lots of different things are formed using this kind of process as well. So there's a lot of interesting stuff they do. Blown film extrusion. So this is how Ziploc bags, trash bags, chip bags, all sorts of things are made this way. Somehow even the super ridiculously loud biodegradable plastic bags that SunChip started using, because they wanted to have the loudest chip bag on earth in in the Guinness records or something. Um, there's an air gas passage that creates this air bubble, and then it gets pinch rolled. So bags, films, sheets, plastic foil, all sorts of things like that are done that way. The fibers are categorized with a length to diameter ratio well above 100. So typically that's used in textiles, so high strength textiles, high tensile strength, high degree of crystallinity, and polar groups in the structure. Spinning is another one. So extrude the polymer through a spinneret, which is a die. This was a process that was inspired by the way that spiders make silk, which is why it's called a spinneret. And these spun fibers are drawn under tension, leading to highly aligned chains and a fibrillar structure. Coatings, thin films applied to surfaces, paints, varnishes. The hydrophobic coating, for those of us that are doomed to wear glasses because of computers destroying our eyesight. The phase change coatings that darken and all of those sorts of things. Scratch resistant coatings are all different polymer layers of different types on those films, which are also, those are polymer films on top of a polycarbonate lens typically. Very rarely is glass actually used. So polycarbonate, which is very hard and very tough, coated with this other stuff to do cool things with. So it can also be decorative and improve the appearance. So you can also have electrical insulation for coatings and things like that. So one of the newer trends is to have silicon coated wire because it's polymer that ages better than some of the materials that we have been using. So we got away from cotton wrapped wire because that was turned out to not be such a good idea. We're using other polymers now instead of natural polymers, and we're coming up with better and better ways to do that. Adhesives is another big one. So this is something that bonds solid materials together, typically using secondary van der Waals forces. So if you've ever put a screen protector on your phone, which probably many of you have at some point in time or another, you know that there's kind of a sticky stuff on the back, but it isn't glue. It's actually a polymer. It's a silicon polymer, polydimethyl siloxane, PDMS, and it's a glass-like silicon polymer that, or silicone polymer. Silicon is different. Anyway, secondary van der Waals forces attach those to the glass surface. You can also get mechanical types, so penetrating into the pores and crevices. So that's where something like a liquid nail type material is going to form a more mechanical kind of bond as it cures. So it penetrates down into pores and then locks in to hold on to those. Films are typically by blown extrusion. Foams are gas bubbles incorporated into plastic that they polymerize. And then there's other examples like the ultra high molecular weight polyethylene that's used as the cup, for instance, the acetabular cup or the substitute for the acetabular cup in the implant world for hip implants. They have a very high impact strength, resistance to wear of abrasion, very low coefficient of friction, meaning they are high lubricity, meaning self-lubricating surface. It's also used in variations of bulletproof vests, so there's a lot of ultra high molecular weight polyethylene used in polymer plates now that are getting to be a lot better than some of the earlier versions are. Wouldn't trust one from 20 years ago. Recent ones are a lot better. They're bulky, but they're a lot less heavy than an equivalent protection level with a steel plate. So There's also things like golf ball covers, and the Acetabular Cup. Um, so a lot of things. Advanced polymers, thermoplastic elastomers, something like styrene butadiene, block copolymers. So styrene and butadiene together give you hard and soft compliant domains together, allowing you to have combinations of things that work together, and you have strengths and weaknesses, all of which come together to make things a little bit easier. So thermoplastics, polyethylene, polystyrene, polypropylene, polycarbonate are less stiff. They are lower in overall stress, yield stress. They're lower temperature applications. They are easier to form and recycle, so they are easier to make cheap stuff with. So they are more common. For polycarbonate being at the harder end, polyethylene being at the softer end, and the other two kind of being in the middle. The elastomers, like rubbers, very large reversible strains, meaning they're very forgiving materials. Good materials for things like tires, which deal with all sorts of harsh environmental things and temperature changes and shock loading and all kinds of stuff. Larger stiffness, larger yield stress, larger temperature, higher temperature applications, thermosets like epoxies and polyesters, smaller KC. This kind of helps to set the boundaries for these. Anyway, again, a lot of information to throw at you guys. We're going to incorporate all of that into the final questions in the test. This will at least give you guys something to work with in terms of this chapter. So this is the last one that we're going to study this semester. So congratulations on surviving this particularly unusual semester. The good news is life will get far, far stranger from here. So there's that. Anyway, we're going to do one more review session before the test, and then that will open just a little bit early so that you guys can get it in, get it done, and get out of campus within the Saturday ridiculous deadline that just is what it is. So, yeah, we'll see you in the next one.